Jai to all of you. My name is Dr. Ritish Kumar, and I am going to give a lecture on the topic of Introduction to Antenna, which lie in the subject of antenna and wave propagation. The subject code is BEC 603. Uh, Before the starting of this topic, we need to understand what is the antenna. So antenna is a kind of a transducer that converts electrical signal into the electromagnetic waves and vice versa. So we will study in detail what is the antenna, how it can radiate the waves in electromagnetic waves in the space, the mechanism as well. So starting the topic. First, this is the syllabus of University AKTU, which has five units. This topic is comes into the unit number 3, that is antenna fundamental and definitions introduction, which this unit has some topics like introduction to antenna, basic antennas parameter, beam area, radiation intensity, beam efficiency, directivity, gain, and the radio communication link, antenna temperature, antenna impedance. So we can say this antenna is totally related to the antenna's fundamentals. So the topic of introduction to antennas lies in this unit number 3. And the recommended books which I will prefer, the second one is the JD Cross. The title of this book is Antenna and Wave Propagation, the fifth edition I will prefer. And in the reference book, I can refer the CA Balanis. The title of the book is Antenna Theory, Analysis and Design, Zonville. Is the publisher. So these are the two main books which comes into the subject antenna and wave propagations. So you can refer both these books. So basic of antennas. So basics of antennas. So antenna is a metallic conductor system capable of radiating and receiving electromagnetic waves, as I told you earlier. So in a short brief, we can say antenna is a kind of device or transducer that converts electrical signal into the electromagnetic waves, and vice versa. That means in the transmitting mode, the antenna converts electrical signal to electromagnetic waves, which travels into the free space, while in the transmitting mode, this antenna converts electromagnetic signal into the electrical signal as well. So if I say for the communication point of view, the communication has three main components. The first one is the transmitter, the second one is the channel, and third one is the receiver. So if I talk about the transmitter side and receiver side, so channel can there is a communication link. You can make it by using a channel, which can be a wire channel or wireless channel. So to make the wireless channel, you need to find this device which can propagate your message in the free space. That device is nothing but a antenna. So to play antennas plays an important role to communicate in the wireless communication channel. So we need to understand how it can radiate the electromagnetic waves in free space. So as you can see in the red written words, so antenna is a also we can say antenna is the transitional structure between free space and the guiding device, as shown in the figure 1.1. As you can see this figure, so this is you can see this is a kind of transitional structure. This is a transitional structure in between electrical signal into the free space that is a free space media. So you can see how we can distribute this system into different parts. You can see this is a source section, this is a transmission line section, and this one is the antenna section, and this one is the radiated free space waves. So you can see here, so we can say this antenna is a transitional structure in between transmission line and the free space wave. So you can see the direction of field in the transmission line is upward downward, upward downwards. You can see, so with the help of source you can generate a signal, electrical signals, which has some which has the voltage, and which has some kind of voltage in the form of sinusoidal waveform. So you can see this is sinusoidal waveform. It has a positive polarity and negative polarity. Similarly, you have the electrical E field is positive polarity, negative polarity. This is a positive, negative, and this is positive, negative. So you can see this is a traveling of. So as we know, because if you give the input of so with the help of source, it can there is current along this path, and you know, if a single wire has a current, it can produce the magnetic field as well. So this, if you look, this is an electric field, and perpendicular nature of magnetic field both are exist in this transitional structure. So with the help, as you know, with the theorem of Poynting vector theorem, that is P is equal to E cross H, right? So this theorem states that all the parameters, either P, E and H, all are perpendicular to each other. So you can see this is an electric field, and this is magnetic field, and this is a power flow in a particular direction. So if I say the electric field variation in X direction and magnetic field variation in Y direction, so the power flow would be in the Z direction. So all are perpendicular to each other, and we know that the electric field and magnetic field both are perpendicular by nature. So in this transitional structure, you can say, because of having the electric field and magnetic field, it can have the tendency to produce the electromagnetic waves which are perpendicular to the electric field and magnetic field as well. So this is the section of source, transmission line, antenna, and radiated free space wave. So how it can radiate? There is some requirement to have the radiation in the free space, as we will discuss in the next slide. Next slide. So as you can see here, as I told you in the previous slide, the electric field and magnetic field are right angle to each other, and the electromagnetic waves are propagated through a space over long distance at the speed of light. So antenna has different kind of radiation patterns. So most probably most antenna mainly has the omnidirectional and directional pattern. So in some applications, same antenna may be used for transmission and receptions. For an example, in the radar, there is transceiver. So this can happen only because of the reciprocity theorem. A single antenna can behave as a transmitter or receiver due to the reciprocity theorem, you can see. So this is a simple radio communication link with transmitting and receiving antenna. This is a transmitting antenna. This is a receiving antenna. As I told you, for the communication point of view, you should have three main parts. This is transmission section, this is receiver section, and this is the channel through which information exchange can take place. So this channel is a wireless channel. This is nothing but a free space media. So you can see the receiving antenna is remote from the transmitting, and so you can see this. Uh, as this section we already discussed in the last slide, that this is source, this is a transmission line, this is a transition phase of the antenna, and this is a electromagnetic radiation, electromagnetic waves travels into the free space. So you can see this electromagnetic waves looks like a spherical by nature, and this spherical nature comes into the plane waves. So because the distance between the transmitter and receiver as far as enough, so this spherical waves converted into the plane waves. So you can see here this is plane waves, and these plane waves, these electromagnetic plane waves received by this transition phase of the receiver, and this receiving antenna converts these electromagnetic waves into the electrical signals, and received by the receiver as well. This is the basic phenomena of this radio communication link, which has the transmitting antenna and receiving antenna. So I hope this communication link is clear to all of you. The next part is this all the next part, the this is the communication link, and for the antenna, this is kind of antenna, and the if I talk about the circuit theory, how we can make the circuit of this antenna, so you can make a Thevenin equivalent. You can see the Thevenin equivalent model of this antenna. This is a Thevenin equivalent model where the source is represented by this section, and the transmission line, this is the transmission line section, and this one is the transitional phase, that is antenna section. So you can see here the source has the voltage source, and it has the characteristic, it has the impedance is represented by Zg, and the antenna section has the loss resistance, which is represented by RL, and radiation resistance is RR. It has both part, real part and imaginary section. So antenna has a complex impedance, that is this real part of complex impedance is RR, and imaginary part is represented by XA. The total impedance of the antenna, you can write RR plus RL plus JXA. This is a total antenna impedance is represented by ZA. So you can see here this is a transmission line section, and the characteristic impedance of this transmission line we can represent it by Z0, or you can write ZC as well, right? So Z0 is a characteristic impedance. You can see there is a kind of standing wave patterns happens in between the transmission line section. So how it can happens, how it can generate, how it generates, because you can see this is a characteristic impedance of the transmission line. If this impedance doesn't match with the impedance of this antenna, then there is a condition of mismatch of impedance. And if you have the mismatching condition of the impedance, then you will have a standing wave pattern within the transmission line, as you can see here, and the reflection coefficient is represented by rho is equal to ZL minus Z0 upon ZL plus Z0, where ZL is the load impedance, which is nothing but antenna impedance. You can write it ZA minus Z0 upon ZA plus Z0. If this doesn't match the transmission line impedance with the antenna impedance, then you will have a reflections from the load, that is nothing but antenna, and you will have a standing wave pattern within the transmission line. So to reduce this standing wave pattern, or to reduce the reflection from the antenna, from the antenna, then you will need to match this characteristic impedance of the transmission line to match with the antenna impedance as well. Then you will, if you are able to match the this characteristic impedance Z naught with the antenna impedance, then you will have a minimum standing wave pattern within the transmission line, or reflection within the transmission line as well. I hope this section is clear to all of you, how the standing wave pattern generates. This is only because of the mismatching happen and in between transmission line impedance and the antenna impedance. So you can see here a typical standing wave pattern is shown dashed in figure 1.3. The standing waves can be reduced and the energy storage capacity of the line minimized by matching the impedance of antenna load to the characteristic impedance of the line, as I discussed, as I told you the same before. So now comes the radiation mechanism. So to have the radiation, there is there is a charge acceleration and deceleration must be there to have the radiation. So you can see an antenna is a transducer that converts electrical and electromagnetic energy and vice versa. The basic principle that radiation is produced by accelerated or decelerated of charge. So this is a basic radiation equations. The dot is representing the variation. You can also write dy dt I into L Q dV by dt. So I dot is nothing but the time changing current. L is the length of the current element. Q is the charge. V the time, dV by dt is the time change of velocity, which equals the acceleration of the charge. L is the length of the current element as well. So this is a basic radiation equation that you need to remember. So there is some point that you need to understand the time changing current and accelerated charge radiates the electromagnetic waves. In other words, we can say the stationary electric charge does not radiate and electric charge moving with the uniform velocity also not capable to generate electromagnetic radiations. It is simply stated that to create radiation there must be a time varying current or an acceleration of charge should be there. To create charge acceleration, the wire must be, this is an important line, this is an important statement. To create the charge acceleration or deceleration, the wire must be curved when discontinuous or terminated. So in the last slide you can see, slide, there is a tapering, there is a tapered section, so you can bending the wire, by bending the wire. So due to the bending nature, the charge acceleration and deceleration possible will happen at this tapering section. That's why radiation happens, right? Radiation happens. So you can note it down. To create a charge acceleration or deceleration, the wire must be curved when discontinuous or terminated. The similar things you can see here. The charge is moving with a uniform velocity. There is no radiation if wire is straight, and infinite in extent. As I told you earlier, there is radiation if the wire is curved, bent and discontinuous. If charge is oscillating in time motion, it radiates even if the wire is straight. This is important. If the charge is oscillating in a time varying motion, it radiates even if the wire is straight. I think these all the statements clear to all of you. Again, the same picture comes how the antenna radiates. This tapering section generate or creates charge acceleration and deceleration. Due to this reason, the radiation will happen and it can generate the electromagnetic waves into the free space. So this is a electromagnetic waves generated by this tapering section. This is the antenna section, you can call it, and this is spherical by nature, and at very far distance from this antenna's area, it will convert into plane wave front as well. So I think this one is clear to all of you. The next is the fundamental parameters of antenna. There are various parameter antenna has, such as radiation pattern, radiation intensity, beam area, directivity and resolution, gain, beam width, effective aperture area, and effective temperature and antenna impedance. So we will mainly focus in this lecture about the radiation pattern. So start with the radiation pattern. So radiation pattern is nothing but a graphical representation of the radiation properties of the antenna as a function of space coordinates. In other words, we can say it represents the distribution of electric field distribution, magnetic field distribution, and power distribution in different direction. We can represent with the help of radiation pattern. If I say the electric field distribution, then you can call it the electric field radiation pattern. If you distribute the magnetic field in different direction, then you can call it the magnetic field pattern or H plane pattern. If you if you measure the power intensity in different directions in the free space, then you can say the power pattern for the antenna. In the most cases, the radiation pattern is determined in the field, in the far field region, that is a function of the directional coordinates. So what kind of coordinates I am talking about here? That is a spherical coordinate system, that is r, theta, phi, right? So theta is the elevation angle and phi is the azimuthal angle I am talking about here. So you can see here, this is a 3D radiation pattern. So this one is pattern looks like in the 3D structure, like in this way. So you can see this is a main lobe, as you can see here. First of all, you need to understand this is a phi plane, this is a theta plane, and this is a radial direction, because this is a spherical coordinate system here. So you can see this is a main beam, this is a main lobe, this is a back lobe, this is a side lobe, this is a side lobe, and these all are the minor lobes, we can say. And where you have the intensity is null, then you can call it the nulls you are having into the radiation pattern. So these are the because we are plotting the field components here, so that's why we call electric field distribution in different directions of the antenna, then that's why we call electric field radiation pattern of the antenna. So you can see at phi is equal to 85 and theta is equal to 30 degree, what should be the intensity of the antenna in this direction. So first you take the phi is equal to 85 degree and theta is equal to 30 degree and keep make draw a projection over here, then these 2 points cuts into the coordinate system, and at this point the antenna has some electric field intensity, and this intensity gives in this particular direction. So direction always specify with the help of theta comma phi. If I say at this particular direction what should be the electric field intensity, you need to write E theta comma phi, where theta is the elevation angle and phi is the azimuthal angle here. So these all the point I already discussed in the last slide. So all the things I told you earlier. So these are the simulated result of the dipole antenna over some specific software like HFS and CST Microwave Studio. So this is nothing but dipole antenna, and dipole antenna has this kind of radiation pattern. This is nothing but the omnidirectional radiation pattern. It looks like a apple kind of shape. So if you look from the top view, you will have a circle, and if you cut it down in between some other planes, then you will get a direction radiation pattern. So this kind of radiation pattern is called omnidirectional radiation pattern. Omnidirectional radiation pattern. So all the things I already discussed in the last slide. What kind of, why we call the power pattern, why we call the field pattern. Field pattern has two different patterns. For the first one, E plane pattern and S plane pattern. So if you draw the field intensity in terms of E field, then you can call E pattern. If you plot the field intensity in magnetic field, then you can call it the H plane pattern. So these are all the terms are clear to all of you. So what is the meaning of normalized field pattern? If you divide the electric field intensity with the maximum field intensity, then you are normalizing the electric field pattern with its maximum value of the electric field pattern. Then you can say this is the normalized field pattern. Similarly, if you divide, or if you correlate or divide the power pattern with the maximum value of the power, then you will have the normalized power pattern in the radiation pattern of the antenna. What is the beam width? So before the definition, first you need to understand this is a kind of radiation pattern as we discussed in the previous sections. So this is a radiation pattern, and this one is the main lobe. So you can see the terminology of HPBW, that this is nothing but half power beam width, half power beam width, and FNBW, first null beam width, first null beam width. You can say first null beam width. What is the meaning of it? So as you can see, the angular separation between two half power point is known as half power beam width. So these 2 points are the half power points. Why you are looking here, why it is written 0.707? Because this is the E field pattern we are talking about, because we know that P is equal to E cross H. If you make the half power point, then you need to take E by root 2 cross H by root 2, then you will have the half power point. So 1 by root 2 is nothing but 0.707. So in the field pattern, you need to take 2 points which has the value of 0.707 of the maximum value. This is a maximum value. If I talk E max, then this one value is 0.707. 707 Emax. So this angular separation gives the value of half power beam width. This is a half power beam width. If I talk in terms of power pattern, then you can make it the, you can take the 2 points, exactly the half power of the maximum. This is P max, then this one is 0.5 P max. It gives the half power points, and this is a half power point, half power beam width. So these all the points I discussed in the previous slide. This one is a major lobe. This is a functional beam width, half power beam width, back lobe, side lobe, also called as minor lobes as well. So these all the terminology I already discussed in the previous slides as well. This is a different kind of radiation pattern. We have the isotropic radiation pattern, directional radiation pattern, and omnidirectional radiation pattern. So isotropic radiation pattern is nothing but a kind of antenna, or we can say this is a kind of idle antenna which radiates equal power with equal intensity in all the directions. If I talk, so in the direction antenna is a kind of antenna which radiates directionally in particular, which radiates high intensity in the particular direction, then we can call it the directional antenna. If I talk about the omnidirectional antenna, so omnidirectional antenna has the isotropic nature in one plane, while in other two principal plane it has the directional nature. This kind of this kind of behavior of the antenna can lie in the omnidirectional radiation pattern. So these terminology is very important to understand the radiation pattern of the antennas. So these are the referred book that I already told you before starting the topic, and thank you.